started, and then my camera software stopped. A part of my microphone, a piece of my microphone, I didn't bring with me, and so the sound today won't be as good as usual. But if there's something you did not hear, just tell me. Okay, is it fairly clear right now?
I can hear you pretty good.
Okay. I try to place the computer closer to me. However, I had planned to do 2 demos at the beginning of class with the Van de Graaff, and I think I'm going to put those off till the end of class because I don't want to have the Van de Graaff real close to the computer. Because I don't want to mess up my computer more than it's messed up right now. Okay. Some announcements. The multimeter quiz is due on the 3rd. Chapter 25 is due on the 6th, and you have an exam on the 8th. Okay, so these are the items that are due over the next couple of weeks. Okay.
You're just a little more muffled when you walk away and turn towards the board.
Okay, I'll try to make sure I turn toward you guys when I speak, and if I forget, just let me know. Okay, I'm sorry. The worksheet. There's a mistake on the worksheet, and I'll fix it today. I'm going to add a day to the deadline for the worksheet. I have to decide how I want to make the change. There's a mistake in it. The density should have looked like this. Okay. Otherwise, the density looks like that. The electric field is 0 everywhere outside the slab in that worksheet. So I'll fix that. All right. If I decide to keep it as the absolute value, I'm just going to double check my answers are correct. Then I'll just tell you guys it's the absolute value. That's Q. Otherwise, I'll change the exponent. It turns out if the exponent is odd in the charge density, the field will be 0 outside. Okay. So I'll probably give you another day on that. Then you guys can ask me questions Thursday on the worksheet. Okay. Today what I'm going to do is talk about equipotentials, and I want to talk about how you calculate the electric potential, and go through some applications if I have time. Okay. Any questions before I get going? I'll get started. So let's review what we talked about last time. So we defined the electrical potential. We defined it as the work per unit charge that an external force must do on a particle to move it between points A and B. That's also equal to minus the work done by the field over Q. The negative of the work per unit charge done by the field as you move a charge from point A to point B. Independent of the path. Okay. We were able to do that. Well, we're able to define the delta U because the electrostatic field is conservative, just like the gravitational field. And yeah, this is an abstract concept, but it will allow us to do problems, a little bit more problems. Okay. The unit for this is the volt. And a volt is a joule per coulomb. Okay. 1 volt volt is 1 joule per coulomb. And so V itself, instead of writing it as delta V itself is the whatever the potential energy is at some location in space divided by the value of the charge. Okay? And I'm going to skip
Although
the
the
videos because of copyright issues. There's one more, sorry. We looked at the case where the electric field was uniform, and we deduced the fact that the electric field is directed towards decreasing potential. Okay, because we showed that E, for a simple case where the field is uniform, we said that E is minus delta V over D, which tells you that the electric field points in the direction of decreasing V. And so to make this a little bit more clear, I'm going to do a little bit of thought experiment. Conceptual question. I want to consider the following. Now I'm going to write these equations over here, so I want to keep them here, but then I got to use the board to write. So just give me a second. Let me rewrite these equations. Okay, so let's say we have a proton, and the proton's moving to the right. The electric field points to the right. What's going to happen to the proton? You tell me, what's going to happen to the proton? Is it going to speed up or slow down? That's the question. You don't know. You can know some of the forces on the protons. The only force on the proton is the electric field, which feels to the right. And according to this, according to Newton's second law, this is equal to ma. For A is QE over m. So the acceleration is going to be in the direction of the electric field. The acceleration is to the right. If the acceleration is to the right and the velocity is to the right, what happens to the speed? So, Scott, you got to be careful because the force is in the direction of the velocity vector in this case. I think you're talking about the electron. Okay. Your statement's correct, Scott, if we're talking about electrons. The acceleration is in the same direction as the electric field because everything here is positive. That means that if the velocity vector and the acceleration vector are in the same direction, the object has to speed up. Yeah, Scott, it's only for electrons, right? If it was an electron, then this would be negative. A would be in the opposite direction of electric field. Then you have a velocity vector pointing to the right, acceleration vector pointing to the left. That would mean the object would slow down. Okay, so this thing is going to speed up. It's going to go faster. What does that mean? So we know photon speeds up. And we know that delta U plus delta K equals 0 from conservation of energy. And we can say delta K is minus delta U. So that means this is positive. Delta K is greater than 0. Because it's speeding up. So what must be true of delta U? Positive or negative? Okay, this is from conservation of energy physics 205. Well, if this is positive, this whole thing has to be positive. That means delta U is less than 0. And you should be familiar with this, because if I take an object, like this marker, and I raise it off the surface it was on, and I drop it, it speeds up. Well, what happens to its potential energy? It decreases. As the object falls, the potential energy decreases. That's because it's speeding up. When the proton speeds up, the potential energy will decrease. It's an idea. Just a different scenario. So delta U will be 0. So the next question is, if delta U is less than 0, what about delta V? Well, this is negative, this is positive, this has to be negative. So V is going to decrease. The object is moving in the direction of the field, but it's also moving in the direction of decreasing V. Okay. The object is moving in the direction of decreasing V. So you can see that the electric field is directed towards decreasing V. Make sense? Personally, I try not to memorize all these scenarios. I just try to figure them out. All I gotta know is if it's speeding up. If I know it's speeding up, then I know this is going to be greater than 0. This has to be less than 0. Okay? And if that's got to be less than 0, and the charge is positive, then this has to be less than 0. Now let me change the scenario. Let's do an electron. Okay, so let's change this to an electron. I'll do the electron in red. And this is an electron. What happens here now? So we have an electron moving to the right. The electric field moves to the right. What is the direction of the acceleration? Well, if this is to the right and this is negative, that flips the vector over, and so the acceleration is to the left. So if the velocity is to the right and the acceleration is to the left, what does that mean? Does it speed up or slow down? From your knowledge of kinematics.
Slow down.
It slows down. Okay, so the electron slows down. So that means delta K is less than 0. Then delta U is greater than 0. Now what about this one? Well, this is greater than 0. This is less than 0. What was delta V be?
Less than 0?
Less than 0. Why? Well, because the electron, for the moment, is moving in the direction of electric field. It's moving in the direction of decreasing V. Of course, at some point, the electron is going to come to a stop, and it's going to change direction if it's still in that same field. And when it changes direction, then it's going to speed up. And Scott, this is where, so, what your comment earlier, the electron is going to want to move opposite to the direction of the electric field. So this electron is going to slow down, come to a stop, and change directions and go in the opposite direction. So the electron wants to go towards, really wants to go towards increasing V. It wants to move against the electric field. I think it's important to understand answering this question. Now, we can change the question and say, suppose a proton moves against the direction of the electric field, and then you can answer the same questions. And in that case, you'll see that the proton will slow down and it's moving in the direction of increasing V. But you should go through this exercise for all the different cases. Instead of trying to memorize them, because if you're trying to memorize the answers to this, different versions of this question, you might make mistakes. It's better to understand the answer. Okay.
Professor,
yeah.
our delta V is the change in electric potential, correct?
Correct.
Okay.
Other questions on this one?
Can you hear me, Professor?
I can hear you now, yes, go ahead.
Okay. So I was just wondering, what would happen to a neutron? Would it just stay with the electric field?
Yeah, that's a good question. Because the neutron has no charge, it's not going to be affected by the electric field.
So it's just based on its velocity alone?
Well, no, but if you have a neutron, this product is zero, right?
Mm-hmm.
So A is zero.
But like the velocity would then be constant, right?
Oh yeah,
If it
yeah.
has an initial velocity, okay.
Yeah, you're correct. Yeah.
Because their acceleration is zero.
Yeah, yeah. Its velocity won't change. Yeah, that's a good question. Other questions on this one? Let's do a more of a mathematical problem. And then we can talk a little bit about units. Suppose we have a proton that is accelerated through a potential difference of 120 volts, and I've been very ambiguous about what the 120 means, because I want us to think about what that means. We want to find the speed of the proton after it's been accelerated through 120 volts. Well, it turns out that if it's a proton, we just did the example. If you're going to accelerate a proton through 120 volts, it's got to move towards the direction of decreasing V. And you'll see that when I do the problem. I'm going to use conservation of energy. I'm going to use this equation. Delta U, or minus delta U, minus delta K. Let's say the proton started from rest. Its initial velocity was 0. And we have minus delta U, which is going to be minus Q delta V. I want to solve for V final. Of course, I multiply both sides by 2, divide by the mass, and then take the square root. And then I just put in the numbers. I'll put the V there in a second. I'm sorry, I'm not being careful to say for itself. In order for me to be able to actually calculate this, delta V has to be minus 120 volts. If I can't take the square root of a negative number, I can't have an imaginary velocity. So for a proton, the proton has to go in the direction of decreasing potential if you're going to accelerate it. And that was, we did that example a couple minutes ago. Okay. And if you do the calculation, you get a pretty sizable number. Now, if we did this for an electron, so this is for a proton. I'm going to use red for the electron. If I do the electron, then really the process is the same. The only thing that's going to change is the numbers. If you're going to accelerate an electron, it's got to go against the electric field. You have to make it, the electron's going to have to go against the electric field. And so when the electron goes against the electric field, it's accelerated. But then it goes in towards a direction of increasing V. So this is positive, then this is negative. And then this is a different value. The electron's lighter. And I don't have that value written down, but it's about 40 times greater. Okay. So this is for the electron. So let's take a look at the kinetic energy. I mean, I can write the kinetic energy as minus Q delta V. So let's look at it that way. Okay. And I can say that because delta K is 1/2 mv final squared minus 1/2 mv initial squared. This is 0. The delta K is basically the negative of the change of potential. Or K is the negative of the change of potential energy. So let's look at the kinetic energy of this thing. And let's go back to the proton. That's Q, and then so this is the total energy of this particle. Of course, a volt is a joule per coulomb. So you can cancel out the coulombs, and you're left with joules. But you know, the joule is a small unit when you're dealing with protons, electrons, when you're dealing with microscopic particles. And so we define something called the electron volt. 1 electron volt is 1.6 02 times 10 to the minus 19 joules per electron volt. 1.6 times 10 to the minus 19 joules is 1 electron volt. And so the kinetic energy electron volt is 120 electron volts. It's a very convenient unit. So when you accelerate a proton through 120 volts, or when you accelerate an electron through 120 volts, its kinetic energy will be 120 electron volts. All right, we define it this way because Q delta V is the energy when you accelerate through that potential energy. Questions on that? And you saw the electron volt and the mega electron volt when we did relativity. So now that we know a little bit about the electric potential, and I know it's abstract, and as you work with this, you'll get more familiar with it. How do we calculate electric potential with a point charge? Or due to a system of charges. So now we're going to focus on, for a while here today, focus on how we calculate the electric potential. Just like how we focused on calculating the electric field. I think these calculations are easier because the electric potential, just like electric potential energy, is a scalar. You don't have to worry about figuring out our hats. So these calculations, I think, will be a bit simpler for you. Plus, you've also seen how we calculate the electric field, so you had experience setting up the universe. So we're going to do the discrete charges first, and then we're going to do the continuous distribution. Okay? That's going to be our focus there. But let's look at a point charge. We know that for a point charge, the electric field is K, Q, over R squared. In fact, let me write it like this, now write it as R squared. Okay, and just for simplicity, and again, this is the vector, that the magnitude of the vector that points from the source to the point at which you calculate the field. I'm just going to write it like this for simplicity. Where this just is the magnitude of that vector. This makes it a little bit simpler for us. So if I went to a point P, I determine the electric field by this. And of course, there's also a V associated with this point. Why is there? Because we know that if you have an electric field, V changes in space. Because I showed you earlier that E is minus delta V over D. So when I put a charge in space, we have an electric potential that varies. In fact, we have an electric potential gradient that varies over space. Let's figure out how to calculate this. Okay, so let's go back to what we talked about the other day. We said that the work done by the field is minus delta V, which is minus Q delta V. The work done by the field is the integral of F dot VR, where F is the force due to the electric field. And this is minus Q delta V. So if I solve this for delta V, and I apologize that I started using R's last time, and many of my notes have S's. I apologize. The R and the S are the same thing. They're just a pattern. You're taking. If I want to calculate the field, the electric potential at this location, with this point charge, I have to integrate the electric field into this guy over some path. And it doesn't matter what I choose for the path, because I know that's going to be independent of the path. Because delta V is related to delta U. The work done by electric field is independent of the path. So we'll integrate between points A and B. Now, of course, this is going to give me delta V. It's not going to give me V itself. In the same way as when you discuss gravitational potential energy, its value is determined with respect to our reference point. So if I take this marker and I put it on my table here, maybe I should point this downwards. So here's a marker on the table. What's its potential energy? Well, I can define it to be whatever I want. I can define it to be 0 on the surface of this table. Okay. So I need to define one of these to be my 0 when I do this calculation. I can define it anywhere, but there's a convention we choose. And I'll talk about that in a minute. So I want to integrate the electric field here. A and B are two arbitrary points in space. And I got to figure out what that dot product is. So I want to do the integral of the electric field between 2 points. Over some arbitrary path. Now, we can generalize it to 3 dimensions, but let's do this in 2 dimensions. My path has 2 components. One along a radial direction and one tangent to it. So I can draw my path in terms of one along a radial direction and one perpendicular to it. This is called the r hat direction, and you folks who took physics 205 last semester, you'll learn about the r hat and the theta hat direction. Okay. Instead of using x hat and I had j hat, I think we talked about r hat and theta hat. So r hat is along the direction of the line between these 2 points, and the other direction is perpendicular to it. Well, the dot product of r hat with anything perpendicular to it is 0. And so the only component that we're worried about here in dr is a component that's in the r hat direction. And so this just becomes dr. The r hat dot r hat is 1. And now in a position to integrate this. This is easy integral. You guys can do this easy. And in fact, let me be more specific about my limits. Let me write it like this. Okay. Where these values are measured with respect to the location of Q. The charge Q, you can say, is the origin. Okay. And that integral is easy. So when we integrate this, we're going to get and of course, this is going to be V at B minus V at A.
Wouldn't the KQ also be negative?
Well, remember when I integrate this, did I get a minus 1 out of the integral?
Wait, say that again? Sorry.
When I integrate 1 over r squared, doesn't a negative 1 come out?
Oh, yeah, right.
Yeah, it's easy. The minus signs are always a problem. Let's assume r sub a equals infinity. Okay. So let's assume our first point was at infinity. So this is infinity. Okay. So we're integrating electric field from infinity to some point near the charge. If you're really far away, and the electric potential depends on 1 over r, doesn't it make sense to make this 0? In other words, define V sub a equals 0. And so that makes V sub b KQ over RB. And so then the potential at R sub b, or any point in space, is given by that equation. So if this distance is r, then the potential V is KQ over R. And so that's the electric potential for a point charge. Well, what if we do a sphere? Well, then if we have a sphere, for example, then we get to break up the sphere into a bunch of point charges and then integrate. And we'll do that later. Okay. So this is for the electric potential for a point charge, and this is going to be very useful because it's going to allow us to calculate electric potential for a system of point charges. It's also going to allow us to calculate the electric potential for a continuous distribution of objects that are not very, very large. And that's what we're going to be focusing on today. One of the things to remember is that R really is the magnitude of the vector that goes from the source of the potential to the point at which the potential is measured. This is a scalar. Calculating the electric potential is very easy because it's just a number that you just add, just a bunch of numbers you add together. So, for example, if I have a system of charges, discrete charges, meaning a system of particles you can count. Let me erase this. So let's say we have you want to calculate electric potential at this point with these three charges. We just use the principle of superposition. We say that the electric potential at point P is K U1 over R1 plus K U2 over R2 plus K U3 over R3. You plug in the numbers, you're done. You don't have to worry about vectors. So it's pretty easy to calculate the electric potential due to a system of point charges. Of course, this V is defined such that at infinity V is 0. Because this is something like that when you do gravitation physics. In general, then, if you want to know for a lot of charges, then you can say V to P is the sum of I equals 1 to N of K Q sub I over R sub I. So you can write a code on the computer that will let you generate that sum. Let's look at this idea then to determine how much energy is required to assemble a system of charges. Really what I'm looking at is the concept of electrical potential energy. I'm going to derive the idea of electrical potential energy a different way. I could take the Coulomb force and integrate it and get the electrical potential energy. But I don't want to do that. That's very involved. And I'm going to be doing this for discrete charges. Suppose I have two charges I put in space. How much energy does it take to assemble? How much work do I have to do to assemble that system of charges? So let's say I have two charges. They're really far away from each other, and I want to put them on the board here. I take the first one from infinity and put it here. How much work does it take to bring a charge from infinity here? The other one's pretty far away. We're in an isolated universe. There's no, I'm not doing any work against the electric field. I'm not doing any work against the gravitational field. It takes no work to put this thing there. No work is required to put this object right here. Again, I'm assuming an isolated world. The only thing in existence are the two charges. The second charge is still infinitely far away. Now, when I put this charge here, now the potential due to this charge is K Q over R. So if I'm a meter away from this charge, then, or Q1, sorry. If I'm a meter away from this charge, then the potential a meter away is going to be K times Q1 divided by 1. If I'm 2 meters away, it's going to be K times Q1 over 2. I want to take an object, a second object that's way out of infinity, and put it right here. So that the distance between them is R12. Well, when this thing was at infinity, the potential was 0. At infinity, the potential due to this charge is 0. When it's over here, the potential due to this charge is K Q1 over R12. I want to know how much work is required to assemble this. And I wrote this equation before. The work is done by the applied force, or the external force, is Q delta V. The work that the external force does to assemble this goes into storing energy. In the same manner as if I take this marker that's on the table, I lift it up to some final height, I did positive work to raise this marker. The work that I did to raise the marker goes into stored energy between the system, the marker, and the Earth. Same idea. Some external force, maybe me, I take the object from infinity and put it there. I've done work on it, and then energy stored in the system consisting of these two charges. And I can easily calculate. I just need to know Q delta V. But the work that's required to do this Q2 times V final minus V initial. Well, V initial is 0. Because it was initially at infinity. So it's going to be Q2 times K times Q1. And so W applied. And then this is the energy stored. The initial was 0. And so the energy stored in this system, okay, Q1, Q2. And so that's the expression for that's the general expression for the potential energy stored in the system of two charges. This is the general expression. The other way to do it is take integrate the force, integrate the Coulomb force, over a path, you get the same thing. And that's not in your book. What I did was I integrated the force through the charge. So this is U, and of course it assumes that there's zero infinity. This is U for a system of two charges. It's also the amount of work that's required for me to put this thing together. What if I want to put three charges together? How much work is required to assemble these three charges over there? How much work do I have to do? Yeah, I got to erase these equations. I'm running out of space. How much is required to assemble this guy, this guy, this guy? Oh, let me put some distances. Whatever that comes out to be ends up being the energy stored in the system. Well, to put the first charge there required no work. To put the second charge there requires this much work. So the total work is going to be work to place the sum I'll put the sum of W's required to place each charge at their location in space. Okay? So, the first one requires no work. The second one, we did already. The third one's more complicated. What is this one? Well, I'm going to use Q delta V. Well, what's my delta V? Well, my delta V is the delta V due to this charge and the delta V due to this charge. Now, when it was an infinity, potential energy was zero. So this is zero, that's zero. Because Q3 was really far away. The W3 then, Q3 times the final one plus the final two. The final one is the potential at this location due to this charge. The final two at this location due to this charge. got to take this and put it here. So I'm going to erase all this stuff. Okay? I'll erase it and I'm going to substitute that over here. So the total is this plus this plus this. So the total energy or let me rephrase that, the total work that's required to put these three charges together is going to be and this is the energy stored in the system. The amount of work that's required for me to put that together is really the energy stored in the system. It turns out if the work that's done, if I have to do positive work to assemble that system together, it means that these particles want to fly apart. If I have to do negative work to assemble them, that means that they want to come together. That means U is negative. And if you think about it in terms of an atom, let's say hydrogen, the energy required to assemble this is going to be negative. And that would be indicative of something that's going to want to stay together. If you look at the U, the potential energy for any atom, when the electrons bound to the atom, it's going to be negative. Because if it was positive, then these things would want to fly apart. Because I'd have to push them together to arrange them in this orientation, or in this configuration. So a negative stored energy in the system is indicative of something that's going to want to be stable, or want to be bound, like forming an atom. It's an indication of that. If I have to do positive work to assemble a system of charges, it's going to want to fly apart. So this idea can be used to study atoms, the molecules, the stability, among other things. I'm sorry, Scott, I missed your question regarding infinite work. Can you
Oh no, that was my incorrect response when you asked the question. So.
Oh, okay. I'm sorry.
You're good. No worries.
Because I'm about I'm a little too far away from the screen. Okay. Are we okay with that? And this is one of the reasons why I go over these examples, because I can relate this to you can write this in chemistry and physics. For those of you in chemistry, you've studied the atoms and molecules. If U is less than 0 for a system of charges, then you can have a system that wants these things bound together. It's indicative of that. I won't say it is. If we have a large number of charges, this is 3. I think if we had 4 charges, I think there would be 3 more terms I forget. But if we had like a lot of charges, and we want to find the energy that's stored in the system, you would write it like this. let's say you wanted to do it with using computer code, you get too many of them to do it by hand. You would write a summation in computer code and do the calculation. This is the easiest way to do it. You don't want to do all the individuals themselves. Why is there 1/2 in front? When I write that summation. Why is there 1/2? Well, if I told the computer to sum over I and j, where I is not equal to j, it's going to sum this term twice. Because k, the computer is going to treat k, q2, q3, and k, q3, q2 as different things, even though they're not. So each one of these terms will be counted twice. That's why you have a 1/2 there. With the computer, if you write code to program this, the computer is going to count this one twice, and this one twice, because the computer is going to say 1, 2, and 2, 1 are different. So you got to take that into account. Okay. Now that we've talked about some general ideas regarding electric potential, we can also obtain the electric field from knowing phi. Let's go back and look at how we came up with phi. We define delta V as minus the integral of the electric field over a path. What that means, by getting rid of the integral, dV minus E dr. Isn't that true? If I integrate dV, I get delta V. So dV is minus E dot dr dx and then dx. So the dot product is going to be E sub x dx plus E sub y dy plus E sub z dz. Okay. And if I just look at the x component of the electric field, I take the derivative of V with respect to x, holding y and z constant. So E sub x is minus dV over dx, holding y and z constant. If you had calc 3, you write this as a partial derivative. And we can say the same thing for E sub y and E sub z. Really, dV looks like this. That's how you write dV. And you can write it as a dot product. You can write it like this. That's called a gradient. So E, be careful with the minus signs, is minus the gradient of V. And the gradient of V, or minus the gradient of V, is that. And so you can calculate the electric field by calculating this thing called a gradient. Yeah, you learned this in Calc. You learned the gradient in Calc 3, okay? You do learn the gradient in Calc 3. But that's it. That's what E is. Okay. Let's do an example. Suppose we're given V as you see on the screen. Let's say V is equal to 2,000 plus 3,000x minus 1,500 z volts. Z squared. Let's V as a function of position in space, which is some kind of rate charge distribution. I want to calculate the electric field due to this charge distribution. Okay, so all I got to do then is take the negative of the derivative of this with respect to x. What do I get? Well, the only term that has an x in it is this. I got to take the derivative of this function with respect to x. And that's going to give me the x component of the electric field. What do we get? Notice this is volts. I have a volt over a distance. The electric field is also written as volts per meter. Then I take the derivative of this with respect to y. I take the derivative of this with respect to y, which is 0. And then I take the derivative of this with respect to z. The only term is this one. I got to take the negative of it. That's my answer. I'm done. The calculation is easy. So if you have an electric field, you have a potential gradient. So if you put a particle in a potential gradient, it's going to experience a force. If you have a pressure gradient in air, a change in pressure between my left and my right hand, any particle there will experience a force between my two hands. It's the similar idea. So a voltage gradient means you have an electric field. If you put a charge in that electric field, or a charge in that potential gradient, it's going to experience a force. That shows you the relationship between electric field and
is that a negative 3,000 on the I hat and a negative 3,000 Z on the K hat?
That's going to be a positive. Thank you.
Okay, perfect. Thank you. I was a little confused about that.
There's a negative here and a negative there, right? Thank you. So determining, it's just very easy to determine. It's very easy to determine E from V because we're just calculating derivatives. Okay, that's pretty straightforward. Going the other way around is harder. Okay, but getting E from V is easy. Getting V from E is a little bit harder. I want to say something more about this. And I had this up on the board before. Then I wrote down this. When is this zero? When is that zero? Three cases.
Perpendicular.
Yeah, that's the one that's the one I'm interested
That's
in.
on the slides.
Okay, yeah. That's fine. You're reading this slide, that's good. Yeah, when these two are perpendicular to each other, the dot product is zero. So if you move perpendicular to the electric field, that doesn't change. You can find surfaces. It's not easy to do, but you can calculate surfaces in which V doesn't change for some sort of charge distribution. The easiest one to do is the point charge. So these surfaces where the potentials are equal to each other, they're called equal potentials. So that means that no work is required to move the charge along an equal potential. And it's important. I mean, I remember when I was in grad school, we were talking about instrumentation, and the one instructor I had was pretty old timer. And he was from the days where they didn't have computers to calculate things. And so, they would be designing parts of an accelerator, and they didn't have a good way to calculate the electric field, if you had, let's say, some complicated geometry like this. Let's say this is positively charged, this is negatively charged. These are just metal conductors. How do you calculate electric field? That's a hard thing to do without a computer, because this geometry is somewhat complicated. You can estimate it, but then there's effects on the edges you have to worry about. And so what he said they would do is they would get a voltmeter, they would put one end of the voltmeter here, or at ground, and they would just measure where the potential was the same. They would actually put this on conducting paper. There's some special paper that conducts electricity. They would paint this with a conductor. And then they would measure the locations where V was the same. And then they would draw a line. And then they would find another location where V was constant, but a different value. And they would draw lines. They would connect the dots. The electric field then is perpendicular to those lines of constant potential. And so they would map out right away what the electric field looks like. They do it with instruments. That's why it's important. And we can do this for simple charge distributions. Let me give you an example. Suppose I have a point charge. Let's pretend it's positive. I also use positive charges. Positive charge here. What do the field lines look like? Well, they point away from the charge. So let me draw field lines for this thing. Now, At any point, remember V is K cubed over R. Right? For a point charge. So let me if I draw a sphere of radius R. What's V at any point in that sphere? Isn't it the same thing? V has the same value anywhere in that sphere because of this equation. That sphere I drew, okay, it's a circle, but think 3D, okay? That sphere that I drew is an equipotential surface. Anywhere along the surface of that red sphere, V is the same. So I can put a charged particle and move it around here. It requires no work. So all these spheres I draw are equipotential surfaces. And the electric field is perpendicular to it because we said this happens when E perpendicular to VR. The electric fields are perpendicular to the equipotential surfaces. The surface of a conductor is an equipotential surface. Why is that? Why is the surface of a conductor? So let's say I have a conductor. It can be any shape.
Is this just due to the fact that the conductor can move electrons around freely?
Not necessarily. What do we say about the field at the surface of a conductor? The direction of the field. Isn't it always perpendicular to the surface? When we talked about conductors in electrostatic equilibrium, the one thing we established was that the electric field has to be directed perpendicular to the conductor. It cannot have a component along the surface of a conductor because then an electron would experience a force along the surface of the conductor. And since this is perpendicular to the surface, anywhere if you move perpendicular to the surface, then this has to be zero. And so the equipotentials really for this basically look like this. It's using some physics. They get more rounded as you get further up on it. That's it. So this is a set of, the red lines are the equipotential for my blue conductor there. Okay, because this surface has to be an equipotential because we know that the electric field has to be perpendicular to the surface of the conductor. So this is the field of a uniform conducting plate. If it was rectangle, then the equipotential surfaces would have a kind of a rectangular shape. It would take the shape of the conductor, essentially. As you get further and further away, they get rounded. If I have plane, okay, with a point charge here, This is a conducting surface. I put this guy here. If I put this guy near a conducting surface, let's say this is positively charged, and the electrons are going to be attracted to the surface. The field is going to be perpendicular to the surface, but the equipotentials have this almost the same shape as the surface. As you get closer to the charge, these get more rounded. If you want to actually solve this problem, you have to be in graduate school. And then the field lines have to be perpendicular to the surface. The field lines are always perpendicular to the surface of a conductor. Okay? Gives you an idea what the field line and equipotential surfaces look like. And so that gives you an idea of the system. It helps you to understand the system by drawing these pictures. Okay. I've said a lot about potentials. I've given you a lot of different examples from a theoretical point of view. Now we're going to do calculations. So the second half of the class, we're going to do calculations. So it's about 12. My wall clock is different from my computer clock. It's about 12. Last second. 25. So let's meet at 12:45. Okay. Let's take a break and meet at 12:45. Okay. I'm gonna go eat lunch. You guys should too.